Hello, welcome to another episode of Beam There Done That, again with my co-host Francesco Cesarini.
Hi, I'm Francesco. I'm also co-host, and yeah, today I'm really excited to introduce Lukas Backström, formerly known as Lukas Larsson. And what makes it really special for me is the fact that Lukas was a student of mine at the IT University, which is today part of Chalmers in Gothenburg. Back in 2004. And he was one of 70 students, but he was one of the students who actually went in and completed his Gen server exercises in class. And most students who completed the Gen server exercises were actually offered or we suggested, why don't you apply for a summer internship at Erlang Solutions in London and the following summer. And so 2025, he came, spent the summer in London, liked it so much that he came back in 2006. So it wasn't 2025, it was 2005. So yeah, and he came back in 2006, did his thesis project, and 20 years on, he's still at Erlang Solutions. Since 2009, he's been working with the OTP team, focusing on the Beam. So, Lucas, well, I tried to keep it short and I failed, but why don't you take it from here? And rather than your full CV, why don't you tell the listeners the path that matters, today? How someone who, straight out of university, finished a Gen server exercise and ended up building a career in the Erlang ecosystem and managed to release the just-in-time compiler for the Beam.
Hi, everybody. So I started working with Erlang quite a long time ago now, and it's been I've always been interested in helping building tools for other programmers and developers there. I didn't really start out doing that, but I've always been interested in doing that in various places. So when I started working at the Erlang OTP team, I started out working with common tests and improving those parts and listening to the other people in the team, what they were talking about. They had already been there working on the compiler and the virtual machine and all of the different parts, the runtime system, for a decade or two at least. So there was a lot of knowledge needed to be that I could absorb. And then when the opportunity was given, I started working on the different parts of the runtime and then working on, tracing and various other parts in the runtime, and then ended up also doing a lot of experiments around just-in-time compilers and improving the performance of the interpreter in general using various tricks found in other implementations and so on. And then as time went along and a lot of failed JIT experiments, finally we succeeded with something and we got something working there, which was great fun to do. And we're continuing working on that today, various parts.
Brilliant. So before we get into the JIT, go back almost 15 years now. You joined the team that had been building, the Beam since the 90s. It had its own culture, it had its own way of working, its own way of doing things. And when you came in, what was the most valuable thing you brought with you to the team? And looking back, what's the most valuable lessons the OTP team have taught you?
I think what I brought into the team was probably enthusiasm and a bit of questioning the norm of how things are done and what things you could do and could not do, and working with various parts there. But mostly just enthusiasm and trying to understand what was going on, as most of the team had already learned so much that I did not know. What I have learned, I guess, is mostly the detail and the amount of quality you need in order to build the kind of underpinning software that is there for running something like the Erlang virtual machine, as almost all bugs that you make will be found eventually by somebody and triggered by somebody. So it's very important that you double and triple and quadruple check everything and have good tests and so on, because even small mistakes will come back and bite you eventually. There have been numerous edge cases of various things that I have done that I would never imagine somebody hitting, and then you get somebody there. So it's the details and the quality required to build something like this is really on a different level than what I've been seen in other places there, as so many different people use Erlang in so many different ways, especially now that Elixir has come into the game, 15 years ago now, and started putting new requirements and new things that we need to take care of.
Reminds a bit of myself when I was straight out of university. Oh, Francesco, have you tested this? Yes, I did. And then you go in and someone gets your mouse and presses a link on the UI you're working on, and you get an error. Oh, but I didn't test that. I tested this. So yes, I think testing, it really hits you when you need something where downtime is not allowed. So yeah.
Yeah. Yes, definitely. And also performance regressions are very hard to catch in those scenarios.
Yeah.
So that's one thing we really struggle with is, will this feature impact performance in a way that is good or bad? And depending on the customer, it would be good for some and bad for some. Different users have different profiles. So the performance aspect is really critical.
That's one of the things they don't teach you in university. I agree.
So before we get into, BEAMism specifically, I'd like for us to all be on the same page about understanding about what is the JIT compared to everything else, right? So walk us through it very, as plainly as possible. What is, the difference between ahead of time compilation, an interpreter, and the JIT?
Normally, when you start creating a new language of some sort, the easiest way is normally that you do an interpreter for that language. So you compile, you either just walk the code as it is and read it word by word, so to say. That's something similar to like what Bash does there. So it just reads the words and executes them as they happen in the file that you're working with. And as your project matures, you normally add a compiler on top of that so that you compile to something that the interpreter can more efficiently read. So you get something like Erlang or Elixir, or you get something like, I think Ruby and Python does similar things there. Java does the same thing for various parts there, while JavaScript, for instance, has stayed and they run with the source code directly. They don't have a compiled intermediate that you can run. As you in JavaScript, you get in the browser immediately and you have to run that. Ahead of time compilation means that you take another step in another direction. That means that the next step is that you compile your source code into native code directly so that you can execute it. So .exe files on Windows or just binary files on Linux and BSDs so that you can run them directly. That's a rather big step because you now need to understand the processor architecture that you have there, but you gain a lot of things because you can do a lot of compilation optimizations for the specific hardware, and you can really pin down different things in there. You gain a lot by doing an ahead of time compilation, but the complexity increases a lot. Nowadays, a lot of people use LLVM for this. So a compiler project that Clang is based on, C-Lang, however you want to pronounce it. And that allows you to make it a lot quicker to do ahead of time compilation. So either you go the ahead of time compilation part, and then you need a long time running, and you get what you compile is platform specific. So it will only run on a specific CPU or even a specific operating system, depending on how you compile your things. And you do this step normally to get performance, or you can go the just-in-time compiler route, which means that you have your interpreter and then you convert that to native code during runtime. So when you're loading just your file with the code that you have in the file. If you load it like JavaScript, you convert that to native code as you see it. Or if you're doing something like Erlang, you load the code inside of the BEAM file and you convert that to native code. So you have the JIT approach where you're optimizing by doing it in runtime, or you have the ahead of time approach where you're optimizing by making native code when you're compiling the actual code. And most languages have experiments doing all of the different varieties of this. Java has an ahead of compilation mode that you can do as well. Same with C#. They also have different things to do there. And people have tried making interpreters for normally compiled languages in order to get faster compile times and faster load times and smaller code bases and so on. So lots of people, there's no consensus on which one is the best way to do things, really. They're just different ways of doing the same thing, making the code run faster.
Now, I'm kind of curious, though, because, like, for instance, records, that just came out, right? It's mostly just supported within Erlang itself right now. The JIT, Is that allowed in all the different Beam languages, or something only Erlang can handle?
No, the JIT runs, it handles what's compiled into the Beam file. So it runs for all languages running on the Erlang virtual machine. So that's Gleam, Elixir, Luwal, and all of the different things there. So it doesn't take any of the parts that are, it works for all the different languages, as all languages really compile down to Erlang in the end there. So if you have Elixir, what the Elixir compiler does is that it compiles Elixir code into Erlang code and then takes that Erlang code and compiles it into the Beam format that is then loaded into the emulator. And the same thing with Gleam is that they also compile down to Erlang code directly. So all of the different languages target Erlang. They just don't write files on the disk. They target an in-memory representation of Erlang there. So everything works for all the different Beam languages the same way. It's the architecture and the operating system that is the limit. So we only run on ARM and x86 64-bit, and we don't support all operating systems and so on with the JIT. There you still get the interpreter.
Now, was ASM JIT the JIT that you used to kind of just drop in and start this whole process, or where was the foundations built upon?
We did multiple prototypes or tries before we settled on using ASM JIT. So I think the current JIT is the fourth incarnation or the fourth attempt to make a JIT, and all of the previous ones used LLVM as a backing. So that used that to generate native code, and then we found ASM JIT in order to make it quicker to emit code, because LLVM is kind of quite heavyweight and it takes a lot of time. So you need to gain a lot of performance in order to make it profitable. So it spends a lot of time optimizing and it might not give you as much. But when we use ASM JIT, the actual code when it runs and when it emits native code is very quick, and then we don't need to gain as much by doing the actual code generation there. So I think the number is that generating the code for this versus for ASM JIT versus just running the interpreter, the ASM JIT is roughly 20% slower, something like that. So it takes 20% more time to load code with the JIT than it does with the interpreter. So if you need very fast boot up times, the interpreter is still quicker. But once you start executing actual code, you quite quickly, that 20% is eaten up by the advantage of actually running native code, because the code is roughly 20% faster, and normally you spend a lot more CPU actually executing your code than you do loading it. So it's a benefit quite quickly.
For listeners who've not listened to the previous episodes, in the 90s, the first version of the Beam, so Turbo Erlang, as it was also called, compiled Erlang to C, and then C to native code. It was much, much faster and sequential code. But when you ran concurrent systems, the speed up was not as impressive anymore. But this isn't how we run everything today. How is a JIT different? How is JIT different from that approach? And why doesn't it hit the same walls as Turbo Erlang and the first version of the Beam did?
I wasn't around at that time, but if I remember correctly, the compiling Erlang to C code part had two different problems. One of the problems was that this was an ahead of time compiler, so it compiled everything ahead of time. And it took a long time to compile projects there. It took a very long time to compile one module. So it was prohibitively long. It was not something that you would do in your development cycle. You would do it for production use only there. And also, I believe that the actual memory usage of the code was very large. So one of the reasons that they switched back into an interpreter after using the C version was that the memory usage of the code shrank significantly so that it could fit inside of the systems that they were making in the 90s at that point. And since then, we have the machines that we run have grown tremendously. So we have a lot more memory to use and a lot more there. So the actual code size does not matter all that much anymore. And it does grow when we do the JIT compared to the interpreter. So we do use more memory when emitting native code. But it's also this ahead of time compilation part makes it so that it makes it a lot slower to compile different parts, as the Erlang compiler is rather quick, at least compared to many of the Rust compiler today as well, as it can keep its scope smaller and make further things. So if you were to chain these parts, you would basically make what hype was there instead. So hype is more of something you can compare to Turbo Erlang, I suppose, than what the JIT is, as the JIT is in runtime and very different than that. But hype is the next logical step from Turbo Erlang, more in that sense.
We've already kind of covered this very superficially in our introduction, but take us back to the start of the BEAM ASM. People had talked about the JIT, for the BEAM for a long, long time. What made the OTT team, want to focus on all of the prototyping activities they did? So not only the first prototype, but all of them. And what was the experiment? When did you know you had something which was worth working on and taking into production?
So the experiments that we did were done together as a research effort with SIX, as it was called, the Swedish Institute of Computer Science. Today it's called RISE, which is another acronym that I don't recall the name of. So we did a research collaboration together with them to try to figure out how we could make a just-in-time compiler for Erlang. And the focus was maintainability, so that we could keep the interpreter and the JIT in lockstep more easily. And we also wanted to focus on making sure that we could, for most cases, generate quicker code than we had there, but there was not really a focus on making everything work quicker. So the tools we used there were basically that for the first prototypes, we were analyzing the way that the interpreter worked by using static code analysis in different ways, and then generating JITs depending on that. So it was more of a JIT generating framework there, which worked. It worked okay for when we were doing specific microbenchmarks, but it did not work well when you were running something bigger, like if you wanted to make dialyzer quicker or some of these offline tools that are quite CPU bound that you need to make quicker as well. So those different things, and they were all tracing JITs, as it's called. So they were tracing the execution patterns and optimizing the ones that they seemed to be hot. And that worked great for small execution kernels, but it doesn't work that great for bigger places when you were running code. And we found out that normal Erlang code is rather branchy and unpredictable in the way that it runs when you're running something like RabbitMQ or running the WhatsApp servers or something like that. It's very branchy and it's not something that can be predicted. So if you have 10 branches, it's very likely that you have at least 8 of them that are very as likely to be taken. Instead of a tracing JIT, would have been very happy if there was only one branch that was the one that were taken all the time. So the main breakthrough when we went from doing these approaches was that we switched out LLVM to ASMJIT to make it much quicker to generate code. But we lost all of the different optimizations that come with LLVM. So LLVM has lots and lots of different optimizations that you can run on your code to make it quicker. So we lost all of those, but instead we got a lot quicker compilation time, and we also went from a tracing JIT to a method JIT, which means that we compiled all the code in a function at the time, or rather we actually did it on a whole module basis. And then in the end, we ended up with something where we had all code loaded like that. So the first prototypes we did for BEAM, we were running in a mixed mode, so you could have modules that were JITted and modules that were unJITted, because we did not support all of the different instructions to start with, and we needed to profile and benchmark to see if this was a good approach. And then as we went along, we removed the ability to run in a mixed mode because it was not necessary anymore, and it hampered some of the optimizations we wanted to make. So in the end, we ended up with something where I think the name you want to call it is a template JIT, which is basically just doing copy-pasting a lot of code from templates into memory and then specializing some few bits of it, depending on what we have in there. And as a coincidence, I don't know why, it seems like both Python and Ruby have done something similar, but not identical, basically a year or two after we did the same thing. So there was some breakthrough in how GCC does various things that allow them to start doing JITs. So both Python and Ruby have started doing a lot of JIT work just after we did it. And by now, I think they've done a lot more work than we have on making their JITs better.
I just wanted to reiterate something that you said, which is basically that in order to really have a decent JIT compiler, you remove, all of those kind of optimizations, right? I mean, when you think of compilation, for me, one of the steps of compilation is making it more, better, right? Finding the right instruction sets to run. And you found that basically removing those kind of cleverness advances in the compilation step for the JIT, you've actually made it, better. Is that really the case?
Well, yes and no, I guess, because it all depends on how long your program runs and what you're willing to pay in order to make a small increase in performance. If we were to use LLVM instead and run those, we would get faster code, most likely. But you would have a startup time of the Erlang VM of, say, it would be, I don't know, if you start a big system, it could take a minute or two to start and compile everything. So you have a trade-off there to how quickly you want to have something to start versus and that's a constant trade-off you get in JITs because everything is done in runtime. And that's why most advanced JITs, or all advanced JITs, have multiple tiers that they use. So they have a tier 1 JIT that does the first thing, and then a tier 2, and then a tier 3, and then maybe a tier 4 that does more and more and more heavy optimizations depending on the level, on how used the specific function is. So when a function has run for a very long time, they will take another look at it and say, okay, now we need to apply these optimizations that will take a couple of milliseconds to run. So we do that, and then it runs for more, and then but now we can run for 100 milliseconds doing optimizations, and then so on and so forth. So we started out by just doing the tier 1 or almost the tier 0 part of the JIT, which most JITs have and compilers have. They have this, we just need to get it running as quick as possible stage. And then you migrate on to more complex tiers. So when we are thinking about making the startup time quicker for us, we could, for instance, start reintroducing the mixed mode so that you would have an interpreter as you're starting your system, and then functions are generally converted over to the BEAM JIT as they become hotter. That could save, I don't know, a couple of 100 milliseconds on boot times, which is important for some scenarios, like if you're scripting or something like that. But it's not the normal Erlang system. And then we can add tiers afterwards if we have the capacity to do so while maintaining it.
It almost sounds like you went for the, first make it work, then make it simple approach, rather than the, first make it work well, and then if you really, really have to make it fast. And that is a fairly unusual thing to brag about on a compiler. Why was simplicity the goal, rather than, maximum performance?
Because we have failed a couple of times with the complexity part of things within the previous prototypes there, and the current JIT is, while it's simple compared to other JITs, it's still quite a complex machinery, especially when you start adding all the type-guided optimizations and things we have done after there. But the real complexity lies in the Erlang compiler and what that does with its different analysis parts, because that's one of the, I guess, unique things with our JIT is that we have both an ahead-of-time compiler and the just-in-time compiler parts of the system. So the ahead-of-time compiler in the Erlang compiler does a lot of optimizations already, and it provides hints to the JIT for it to do additional optimizations in there. And if you compare, I don't know, but it's more comparable to Java than it would be to JavaScript or to the Ruby and Python parts, because the Erlang compiler does a lot of the work. And I'm not sure how much the Java compiler does, but it does do some optimizations that are on a per class basis instead of doing it in runtime there. But then in runtime, you can start doing things like cross-module optimizations that we don't do today, but we could do in future iterations of the JIT. We'll see what happens there.
When you're working on the JIT, right, there's going to be some sacrifices that probably need to be made at some point, whether it's small or big. but there's probably always going to be something like okay, no matter what, we have to have these things, and usually it's just a couple of them, but maybe something quite important, right? I remember we had to talk with Bjorn, and I believe for him one of the things he needed was hot code reload is definitely something that's super important with like the Beam records. Now, is there like some things that you like in order to get JIT working and accepted and being used? Is there some hard stops like, okay, we need to have these things, and then we could maybe negotiate on some other features that we can get rid of or figure out what to do?
I think the goal was always that we should have all features that the interpreter have. We want to have feature parity between the two, and we have that today. The exceptions should look the same, and the things that are hard, so the exceptions and the quirky features that are really interpreter features that need to be there, like how NIFs are loaded into the system and how tracing works and how hot code loading, and also how distribution fits into the whole thing when you have different codes running on different nodes and different things in there. So there's a lot of different parts that need to be there, and it was very important for us to have all of the different parts. We didn't want to change any of the test cases just because of this. And I don't think we had to, in the end, accept test cases that very heavily assume that there was an interpreter running under there, or where the timing all of a sudden was off because we were a lot quicker. But there are definitely parts of the features that would have been nice to get rid of so that it would be easier to make the JIT work. Tracing and hot code loading comes to mind, but that's features that are way too important to remove from our system. It's hot code loading has been something that's been discussed for a long time if you want to have modes that allow better optimizations, because we don't allow changing of modules and so on, because you could do a lot of more things if you could assume a stable world with all modules. But it's a very convenient feature to have, if nothing else, just to test patches and various things, and you still want to have it for your local development so that you can get these automatic reloads of your modules into your systems working there and still have the JIT working and getting the performance when you're doing that. So there's a lot of features that would be nice to get rid of, but the features are there for a reason, and we want to keep them as much as we can.
One of the hard rules you set was never ever slower than the interpreter. And this is it's one of the brutal ones because it's something you can't quite guarantee. Have there been times where it nearly broke the system, where you weren't able to guarantee this?
No, not really. I mean, I guess we did break it in some sense, as the boot time of the systems have become slower. So that's one of the things where we had to compromise. At first we wanted to really make it also that we could boot as quickly as the normal thing, but we realized that that was not going to be possible. So we had to compromise there. And when we first released it, there were a couple of edge cases where code was running a lot slower than it was expected with the JIT in there, but all of them were relatively easy to solve once we knew of them. I believe there was something about how floating point operations were implemented or something like that made it slower to start with, but then we fixed that. And since then we've rather spent time on making the interpreter simpler so that it's easier to maintain the interpreter, and then spend all our optimizing time focusing on the actual JIT. And I think that's one of the major shifts as well that has happened since we did the JIT, that all of the focus now is inside of the JIT to make that work, and the interpreter is just something that we drag along to make it work on the different platforms where we don't have the JIT, like 32-bit Linux on all the different platforms. And that's one of the things that we did not imagine really when we did the earlier prototypes with the LLVM. We always had the vision that the interpreter would be the main thing and the JIT would be the side thing that would be dragged along. But now that the JIT is the main thing, it makes things a lot simpler, and it can make us focus, for instance, to make the interpreter the thing that boots up very quickly but might not be as fast, and then you just use the JIT when you need to have that on the platforms that support it.
Beam Asm's kind of whole identity is basically doing the simple thing, and that can already be quite fast and never break anything. Can I kind of summarize it like that?
Yeah, it's a good summary.
Coming back to the targets, right? So you're basically just supporting, at this moment at least, 64-bit for both Windows, or I want to say Windows, but 64-bit for both, AMD 8664 and also for ARM 64. Which platform came first, and what was like the process to figure out like which process, or like which platform to go at first?
So when we did this in back, is it 6 years ago, something like that, x86 was the dominant platform. So it was really a no-brainer to start with x86 there. So it was just about that time that the M1 was released by Apple there. So before, when we started development, all of the MacBooks and everything were x86. All of your laptops were x86, or mostly all laptops were x86, and all servers were basically x86. So it was ARM was not as mainstream as it is today. But just as we released or started getting ready to release our work on the x86 64 parts, Apple announced the M1, and then all of a sudden we realized that, this is going to be a big shift. We are going to need to have ARM sooner than we expected. So we added ARM support just in the release after. So I don't remember the release numbers, but could it be 24 that we got the JIT and then 25 ARM was added, something like that? So in 2021 and 2022, those would be the years there. And then we also had support for Windows added quite early on for x86. So when the JIT was released initially on x86, we had both Linux and BSD and Macs as there and Windows working. And then we just added, the ARM work. But that was John and Björn that did that. I did not do any of the ARM work. I stayed on the x86.
You shipped it, it was faster, and it didn't break anything. If you were on a platform that JIT didn't support, nothing would break because it would just run, it would just run on the BEAM. And that was OTP 24, if I remember correctly, so 2021. Let's, I want to start off by, let's talk about what happened in the 5 years since. Start with the big one you flagged, back then, ARM 64, the Apple Silicon was the motivator. Did it ever happen?
What, to add ARM 64? Yes, we did that.
Yeah, tell us about it. Yeah.
Yeah, so I wasn't really part of that effort all that much, but Björn and John did a great work figuring that out. They spent, I don't know how much it was, maybe 6 months-ish working on developing that. And we started basically just as we revealed the JIT for x86, we started with the ARM work very quickly on after that. And it stressed our architecture to show that what parts we needed to make generic for the different architectures and what we needed to make specific for the different parts, and what parts we could reuse and so on. Trying to think a little bit about maybe if we need to add more architectures in the future, how we would do that in various parts. But mostly the main architecture remains the same of how it does things there. The ARM just has a different way of doing things, and it's constrained in different ways. It has a lot more hardware registers, which helps us quite a bit to make things simpler, while the x86 has quite a limited amount of registers. I don't remember how many it is, maybe 8 or something like that we can use for various work, while the ARM has 16 or 24. I don't recall the number. That makes it a lot easier to dedicate different hardware registers for different operations and arguments and terms and so on when we do the different things. So ARM was, from what I gather, simpler in x86 because it wasn't as constrained, and it has more, I don't know if you want to call it, modern assembly language that you can program it in, which made it easier to work with in various parts.
So now the JIT will cover, two architectures, and they're the two architectures that matter. So, servers in production and the laptops developers use on a daily basis. Were there other experiments which were done, to bring the JIT to other architectures? I know the Erlang Ecosystem Foundation went in and funded a 32-bit implementation. I know the Atom VM has its own JIT compiler. Are there things, are there other interesting ones where you've learned lessons and you're thinking of possibly integrating, and which are possibly even supported today?
No, I don't think we're thinking of adding any more there. We've said before, at least internally and so on, that we might be able to maintain one more architecture. After that, it becomes quite slow, and we need more people to maintain the various things because you need to build expertise in the architecture. And we haven't decided if there ever will be one, or if it will be, what will it be? There will need to be one more dominant architecture, not something that is possibly up and coming and so on, but it will be something there. So we're keeping an eye on like the RISC-V development and seeing how that goes. We'll see. So far, it's not grown enough to warrant adding a backend. So we'll see if we want to add more things. And I guess it also depends on what Ericsson will use on their systems. If they decide to go with some kind of esoteric, lesser known architecture, we'll have to have a look and see what that might be. But right now, there's no plans to add any more, and it's the ARM64 and the x86-64 that are the ones, and they catch almost, I don't know, a number, 99% of all usages, 95%, something like that.
Back in 2020, you said you wanted to keep the JIT simple and push the cleverness into the compiler instead. And one of the things you flagged when you introduced JIT to the world was type-guided optimizations. So feeding the type information from the compiler into the JIT. Has that materialized?
Yeah, that has materialized. So again, it's John and Björn that are working in this area. They've implemented quite sophisticated type analysis inside of the Erlang compiler that tracks all of the different terms and types and figures out limits on integers and limits on tuples and various things, and figures out if a tuple can be safely modified in place instead of copied. So doing escape analysis various parts, and then that information is embedded inside of the BEAM file, so that in some cases as specific instructions, in some cases as metadata to those instructions, and then we get into a scenario where you can, in the JIT, make decisions depending on if it's helpful or not to have that information, so that you can know that if you do a plus operand, you can get rid of checking if it's an atom when you know that it will be an integer. So you can get rid of all of these checks. So when you do a plus of a known integer that is small and another small integer, it will just be a very small assembly operation to do that, when the Erlang compiler has already told you that it's safe to do that kind of parts. And the types are driven into a lot of different parts in there. So the Erlang compiler has become a lot smarter in recent years. It was a big leap just the years after the JIT for the ARM JIT was done, where John did a lot of optimizations in the compiler to do with the type parts. And it's really made some of the parts where you need to guarantee when you're running Erlang code. So if you're adding an atom to an integer or something, you need to guarantee that it will make an exception and not crash the entire VM. Those tests can go away in a way that they couldn't be before. And also the same analysis is used to make the actual compiled Erlang code. So the code that the compiler emits makes that more efficient as well by removing guard tests that are superfluous on internal functions and so on. So that optimization drives both the JIT and together with the compiler itself, makes it a lot smarter. So it's a mini dialyzer, so to say, or type analyzer inside of the compiler itself that does a lot of really advanced checks for different types.
Now, is this the same type information that made native records possible?
No, I don't think you can say that there's any correlation there really at all. The type information for the type, so to say, for native records is different kinds of type. So that's the term type that you work with there, not and that they have really nothing to do with each other.
BEAM also meant the end of something, something I think those who've been around the ecosystem for a while have used extensively, and that is HYPE, the High Performance Erlang project. So the old native compiler. What happened there, and what lessons were you able to take from HYPE and then apply to the JIT?
I'll start with the lessons that we've taken from Hype. So I think there's a lot of the different compiler optimizations that the Hype compiler did. We've taken and then applied them inside of the Erlang compiler instead. So it did very advanced type optimizations, and we've taken those and amended and improved in some cases and put them inside of the Erlang compiler. And various other optimizations that they did, we have also taken and placed inside of the Erlang compiler instead of having it inside of the Hype compiler. And the Hype compiler approach of doing ahead of time compilation was something where it was, as it was opt-in and you didn't get the cross-platform benefits, we found that not as many projects that we wanted used the Hype compiler. And to add to it, we also didn't have any knowledge really to maintain or support the Hype compiler. Nobody at the team knew how it worked, and we knew it had bugs that caused the emulator to crash, and we didn't have the capacity really to maintain or get the knowledge to fix the different bugs that were in there. And it also made various trade-offs in terms of what features it allowed. So I don't believe it allowed you to reload its code, at least not without leaking memory, and various things that could have been fixed, but we decided to go another route as we wanted to make both the loading into runtime instead, so that you didn't need to do cross-compilation of Erlang modules as you would have to do with Hype. And you also weren't bound, the Hype code was also bound to a specific version of an emulator, but we wanted the code that we were running to be able to use so that you can compile it with an old compiler and still run it on a new system. And ultimately, the reason why Hype was removed at the point with the that we had introduced the JIT was because we rewrote the code loader inside of the virtual machine significantly when we did the initial JIT, and Hype was all over the place inside of that loader, and we decided that we did not want to port all of the work with the Hype loader inside the work that we did together with the JIT. So we decided that this was the time that we should drop support for Hype at the same time, so that we didn't have to do the work to introduce it into the loader again, and possibly also figure out a model where we could run Hype code inside of the JIT, which would also be problematic, though probably doable. All of these things are doable, but it would take extra time to do that. We decided that it was not worth it since we were betting our money on the JIT at that point.
When you first introduced the JIT to the world, you said it was production ready, but you didn't know of anyone actually running it in production. I want to go in and actually share a tweet from the head of WhatsApp here. Let's see if we see it, where basically launching the JIT allowed WhatsApp to reduce its server needs by 25%. That is huge. That is absolutely huge. What have you learned from it actually being everywhere?
That it's good the way it is. We haven't seen that many people haven't had issues with it, since it just makes things quicker. There's been no complaints about the boot time there. I don't think people have even noticed that it boots slower. And in all of the different production usages, there have been relatively few bugs in the actual JIT we have found. There are, of course, bugs that we have fixed, but they are far and quite few, or between a few. And I'm sure there are still some bugs that we have not yet caught in there with the interaction with the compiler and so on. But it's been fun to see. It was fun. It was a fun couple of years when everybody was migrating over to the JIT and getting a lot of performance increases. I know that there's both the RabbitMQ fleets and the people that are running RabbitMQ as a service and so on, and various other parts. They really enjoyed getting that extra boost of performance just for free by just upgrading versions. It's one of the versions where we have not had to drag people up to. Normally when you upgrade a version, people are like, yeah, we'll upgrade in a year or 2 or 5, because there's no big benefit for them. But for the JIT release, everybody was jumping. I know WhatsApp, we released the JIT in a major version in May, I believe, the year after, but WhatsApp was using the tip of the master branch for the JIT from the day that we released it, based almost there. So they were tracking that and running it in production. And then when the actual release came, they were using the tag release, which was almost like 9 months later when we fixed all the bugs that we found along the way. And there were a lot of other things, users also using the master version for a long time before we released the actual JIT there officially.
BEAM ASM and the JIT wasn't built in isolation. You learn. You stopped prototyping with LLVMs and you started leaning on ASM JIT. So ASM JIT is an external project. Can you tell us a little bit more about it?
ASM JIT is a toolkit to build just-in-time compilers. It has some users, but not a lot. So it's a big project, but it's run by one person that has done a lot of great work. And it has multiple levels that you can use. So you can use it as a JIT compiler, and it will do some optimizations, I believe, and register allocations and so on. But we are using it basically as a assembly emitter. So we just call it it's a C++ API that we call in order to emit instructions to make it work. So it's a rather thin layer on top of just emitting the instructions. And then we have some tools in there, like we use its memory allocator in order to allocate memory for the JIT. It makes it easier to work with cross-platform so that we don't have to care about how to do it on Macs and Windows and Solaris and all of the different things that we try to run on. I don't actually know if you run on Solaris. Maybe we do. I don't recall. For different parts. So it makes things a lot simpler, and it made it very simple to prototype the initial parts without having to learn the actual decimal numbers that you need to do and the different encoding parts of x86, because x86 is very old architecture and a lot of complicated parts, and you need to use different instructions depending on the type of the arguments. You need to put different prefixes and suffixes on the different parts, and the ASMJIT just solves that for us. So it calculates, given that you have a register and a address of a certain size, you need to use a certain variant of the instruction, and otherwise you need to use another variant. So it helps with a lot of the complexity of emitting these parts. And it has a bit of an overhead, but very small compared to a lot of other parts. Unfortunately, the person that works on it cannot really spend as much time as he has before, as he has to make a living as well. And there's unfortunately very little money to be made on making open source JIT compiler infrastructure projects.
Can you talk a little bit about the cooperation, with RISE, but also with the OTP team, who helped out on the compiler side? Who was Björn involved?
With the original x86 parts, we didn't do anything, or the ARM as well. We hardly did anything in the compiler, the Erlang compiler. So we just took the code as it was and then translated that. And that was me and John working on that. I did the initial small prototype, and as soon as I got something working and that looked very promising, he jumped aboard and we did the x86 parts together. And then Don Gudmundsson did the Windows part of all those for x86. And then as the JIT moved on, I moved on to do other things, more developer experience parts of Erlang, and left the JIT work to John and Björn. As for the earlier parts of the JIT experiments, we did work with Six at that part, and that was together with a colleague called Ray Dreihammar that did a lot of work with trying to automate various parts there. He later moved on to work on the Erlang compiler instead of working on the JIT, doing various optimizations for escape analysis and the different parts inside of the compiler. So it's a small team that is working on the different parts. And nowadays we also have more people getting into that part.
I was going to say, just to kind of wrap up before about the ASM JIT, right? So it sounds like it's mostly one guy's work that, the OTP team is standing on to kind of do even greater things, and everybody else is kind of dependent upon that. So it's almost like a upside down kind of triangle where you have the tip, which is the guy who was working on the ASM JIT. Then you have the OTP team, which is, near the tip. And then finally, all of us users of the BEAM are basically the bottom part of that triangle that's been flipped. Is that kind of like a way that we could say that?
Yes, I suppose you could say that. But nowadays, John has become a maintainer of this ASM JIT part. So we are part of maintaining it, but we are just maintaining it for our purposes, so to say, and helping out there. So we have semi-adopted the project. They're not fully, but we help out where we can in that project. But it's hard being the one guy developing and getting money for those parts there. But it's very stable and it works for our needs perfectly there. And the only issue really is if we were to add support for another architecture that is not supported by it, we would need to look into how to do that and get that working. But for us, it's been great working with that toolkit to build JITs.
Yeah, let's fast forward to something current, the Atom VM. So it's the virtual machine that runs BEAM languages on microcontrollers and in the browser. And it's now getting its own JIT compiler. And the team behind it has very openly said that they're following the BMASM playbook. And they have to keep it simple because the team is much smaller than what than the OTP team. In fact, I think it's only one person actively working on the VM, and they're doing it in their own time. So what is it like watching your design philosophy get picked up by another virtual machine?
I think it's great, but I don't know how much credit we can take because we are not the first ones doing something like this. Doing template JITs in this way has been done for a long time there, and it was just a matter of us trying one of the approaches that have been done for doing this and getting it running. So it's I think for all JITs, it's a pretty natural way to start with making it very simple translation and seeing if you get anything from that. And it's a rather big complexity step to just do that, and then you spin and iterate on what you get from that approach. And I think that's where most JITs most likely started out, doing a very simple translation and then doing it more and more complex as you move along and get more people to work on the program and get more time and so on and so forth. I had a look at what the Atom VM implementation was just yesterday, and I'm really amazed at what he's managed to do. So many different platforms and the instructions and so on. Getting that out, it's really impressive.
We'll be inviting David soon for an episode on the Atom VM coming sometime in the fall. But this story goes to say something about how the Erlang ecosystem is evolving. It's not just one virtual machine, but a family of them all sharing ideas, and that's really great to see.
Yes, and it's been more, there's been a lot of different virtual machines along the way. There are things like we had what was called Erlang for one point, Erlang running on the JVM,
Okay.
which was a rather big, ambitious project that almost got compatibility and was a lot faster than the Erlang virtual machine at the time. And I would imagine if you can still get it to run, it would still be quicker than what we have built today. But it's of course compatible with Erlang. I don't know what it could have been. 13, 14, or something like that. 17, long time ago. And then keeps popping up like Ling VM getting their things, and then the Atom VM. So it's nice to see that people are experimenting with writing virtual machines. It's a lot of fun to write virtual machines.
We've traced the arc, right? Ship something simple and always, faster, right? Then extend it carefully. We've had ARM64 support. Type guide optimizations, the compiler feeding the JIT. Looking forward, like what's the next phase? Like where does the JIT compiler go? I'm sure there's more things that could be added to it or removed, or maybe start to actually add in some optimizations that you're basically supporting at least two architectures.
Yeah, I think the native record work will start to drive us to make some more optimizations in runtime than we have done before. The most obvious one that we might be looking at is to do inline caches of various things. So caching common operations to know what they can do. So if you do a lookup into a native record of some sort where you don't at compile time know exactly the layout of the fields, we can do in runtime, you can figure out that this key is exactly at position 3, and then we can do some optimizations based on that and adapt the code as it's running to figure out those parts there. Otherwise, it's always tempting to look and see if we can do a second tier to our JIT so that we can do an optimizing JIT on top of this, so that if a function is called enough, we will compile that using more optimizations, and most likely those optimizations will be inlining things so that we can inline cross modules in various parts. But that's a significant step up in complexity, but it's a nice project to kind of think about and wonder how that would work and dream of a time when I would have the time to work on it.
Kind of going back to your design of the JIT, right? You have this whole idea of keep it simple, but at the same time, as you're just admitting, is that when you add optimizations, you do get some performance, some performance out of it, but also there's a little bit of a tax you have to pay. Every performance win is also is great to have. How do you decide how far you want to go without causing too much of a tax on the users of the Beam versus actually giving them a win in the long run?
I don't know. It's hard to do. You have to be mindful of how many people are maintaining it and trying to figure out what you can do and the various parts. Making something that is very complex and few people know is very vulnerable. And if those people decide to do something different or move away, you will get a lot of technical debt that nobody will understand what is going on and what's happening. So you have to be very careful when you move forward there. So it's a hard compromise to make. And we started out saying that we will never optimize the JIT, and maybe we won't. We will see where the future leads us. It also depends a bit on how much help we can get from various tools and so on to help analysis in there. And if there pops up something different than ASMJIT, because ASMJIT will not do any optimizations for us. So if we have some kind of tool that would help us with optimizations, they are exploring something like Crane Lift, which is a Rust JIT framework, or going back to LLVM again, seeing what they can do and maybe lifting some of the complexity into their code instead of having it in our code. Could be options, but they are not perfect tools that are custom made to our project and our problem. So it will be different there. And we also have a rather unique way of running things, as we have millions of processes running the same code. Normally you have a system that is running only like 1,000 threads, maybe a maximum running the same code, but we have so many different processes running the same code and using the same standard library in very different ways. That makes for a quite unique challenge in order to JIT the best version of the different code. So we will see. It's a constant compromise to figure out.
You teased it earlier, we teased it earlier, the JIT philosophy is spreading. So the Atom VM now, and maybe other VMs in the future. Does the future of, fast Beam code, get fragmented as a result of this across multiple VMs, or does it actually converge?
Oh, I don't know. I think it's better to have multiple VMs as we can experiment with different ideas in different ways. And they, like the Atom VM and Ling, have had very different targets than what we have. And all of them have been for smaller systems there, except maybe the Erlang VM then, that would be for larger systems, that it had a lot slower startup time. But once it got going, it was really, really quick. So maybe the next experiment that somebody will do is build a VM that is actually quicker than ours, based on, I don't know, Graal, maybe, to see if we can run something in there or compete with Clojure's, what do you call it, agents framework that I forgot the name of, and see how that works on the JVM or something.
Lukas, for the listeners who don't actually work on the Beam, but you want them to basically remember something about this whole podcast and what we talked about and all the work you've done on the JIT, what do you think you could kind of wrap up your work on the JIT in this podcast and kind of let them say, okay, from this whole conversation, just remember this piece?
I don't know, the JIT is great. It's quite relatively simple. So if you want to have a look at how it actually works, you can quite easily just fire it up and it will dump the different assembly. You can dump the different assembly files and have a look at what your code actually gets generated into, just to get a start of seeing what it looks like. And the translation is relatively straightforward from at least simple code into assembly code, given that you can kind of read x86 or ARM assembly. So having a look at it, and it's a lot of fun to work on these projects. So I would suggest having a look, as it's probably one of the simpler JITs, and you can quite easily get your head around how it works if you spend a day or two just digging through the parts. And it's an exciting piece of machinery.
If people want to follow more of the work happening on the Beam or even within the JIT itself, where can we best kind of follow to see what's going on?
So I think I would say the same probably as Björn says. We have a blog on erlang.org that you can follow. We used to post a lot more than that we do nowadays, but it's if something exciting happens, we do a blog post there talking about the different parts, and otherwise it's following the GitHub pull requests and seeing what happens and checking for the JIT parts and seeing what optimizations are made. Mostly the work nowadays is done towards the compiler and not the JIT for the optimizations, various parts. But the native record implementation obviously touches all parts of those things. So if one wants to have a look on how you introduce a new data type into the system, having a look at those commits is a good starting point.
It's time to wrap up. 20 years ago, Lukas was a university student of mine. He was working on his Gen server exercises. And today he is, writing and maintaining the code which runs underneath every Erlang and Elixir system on the planet, quietly making them all faster. So almost, almost saying an unsung hero. And he did it not by being clever, but by being disciplined enough to do the simple things that always work. So first make it work, then make it beautiful. And by doing that, he actually made it fast. So if you're new here, this is what the Beam They're Done That podcast is all about. It's about the people who build the foundations the rest of us all stand on. And it's all about the hard-won judgment that goes into them. So if you enjoyed this episode, you'll go in, hit subscribe. We've got an episode on alternative VMs in the making, as well as one dedicated to the Atom VM. So thank you for listening. And for the record, this episode was recorded on May 27th, 2026.